Christmas time.
Okay, welcome to Math341, lecture 31. So what we're going to continue with today is applications of the material we're doing. So this is a nice way to review the material and to get a sense of why we're spending so much time, as well as to see what would happen if you go to future math stats classes. Where does this material go? Out of curiosity, how many of you have seen anything on Benford's Law before? You are not eligible then to answer questions about expectations of things, at least in the beginning. Okay, so motivating question. If you have a nice data set, such as Fibonacci numbers, stock prices, street addresses, what percent of the time do you think the first digit will be 1? So if you just guess naively, what would be your first obvious guess? What percent of the time?
11%.
No. Try again.
9.
No.
10%.
10%. Your first guess is 10%, right?
But you can't start with 0, right?
You didn't realize that at first. You start off with 10%, right? All digits are equally likely. Then you realize you had a brain freeze. Now what would you change your guess to?
Like 1/9.
Now you change it to 1/9 or 11% because you can't start with a 0. Okay, but the first natural guess that a lot of people will do is 10% because they won't think of zeros. Yes?
Why couldn't you start with 0? Isn't there a stock price? It's 0.
No, because you're talking about the leading digit. So if your price is 0.0013, you'd write it as 1.3 times 10 to the negative.
Street addresses with the 0 in them?
Street addresses, you would not have a 0 as the leading digit. You normally drop the leading digits, and you'll use scientific notation. So you would never write, somebody lives at 00132 Cherry Lane.
I'm sure someone has an address like that.
You normally don't have leading zeros. You normally do not. Now, sometimes in computer science, you might append things in an array, and you might have a couple of 0 elements in the array, but when you write numbers down, we will be talking about, in scientific notation, the significand, and then you'll have 10 to a power, and that will tell you where you put your decimal point. So your thought experiment, fluctuations, the data shouldn't be perfect, about 11%. It turns out in many situations, about 30% of the time, you will have a first digit of 1. And only about 4.6 of the time will you have a first digit of a 9. So this is called Benford's Law. It applies not just to the first digits, but first 2 digits, or in fact to the first however many digits you want to look at. These occur in a lot of different places. One is the Fibonacci numbers, seeing about 30.1% for leading digits of 1. Another is most common iPhone passcodes. Do not ask me where I got this data from. It's nice to have friends at certain organizations. Twitter users by the number of followers, distances of stars from Earth. There's a lot of things where you have this prevalence of having more observations with a low leading digit starting than a high leading digit. And what gets better is the more data sets you amalgamate, typically, the closer you get to this Benford's Law of digit bias. So today I want to explain a little bit of Benford's Law. I want to discuss some examples and applications. I'll sketch some of the proofs, and if you're interested in more details, let me know, and I can give you some papers to read. If you are really interested in doing math research, these are some topics I work with students over the summer, and as time permits, I will talk about some work I've done with students in small on these, some open problems. All right. So just to give you a little bit of a warning, I was contacted years ago by someone from the IRS, and the email began, "Greetings, my name is so-and-so. I'm a senior criminal investigator at the Internal Revenue Service." I was like, oh. And it took a while before I could read the next line of the email, which was, "I just read with interest your recent paper in Acta Arithmetica." And I was such a young, newly minted PhD that, wow, somebody actually read one of my papers? I didn't even care that it was with interest. So the IRS is very, very interested in detecting fraud. For good or for ill, they only have finite resources. So they want to try to determine where should they allocate them. What is more likely to be fraudulent? We've talked a little bit about if you flip a fair coin, or if you just randomly try to make up a sequence of heads and tails, if you know some math, you can distinguish. Most people will be good and have about half heads, half tails, but they won't be so good about runs of heads and runs of tails. So frequently the IRS does use stuff like this to detect possible fraud. It doesn't mean that fraud has happened. It just means with a finite amount of resources, this might be a good thing to investigate. So I emailed Scott Adams for permission to use this. Your travel expenses are rejected because all of your meal costs are round numbers. You're a liar or worse. I decide what to order based on what totals to a round number after a 15% tip. That's worse. So there can be alternate explanations besides fraud, and it's important to remember that. Right. lot of different places where Benford's law occurs. Now, the fact that over here that we have products of random variables, you can begin to see why we might care about that in a class like this. Differences of order statistics, financial data, hierarchical Bayesian models, okay, starting to see some statistics and applications. Recurrence relations, these are discrete forms of differential equations. They model so many things, this begins to give a sense of why this occurs in so many different places. Here are three of my favorite applications. One is analyzing round-off errors. Another one is determining the optimal ways to store numbers. Any CS majors here? How many of you have read The Art of Programming? None? Famous book by Donald Knuth. He actually has a section in Volume 2 where he talks about Benford's law precisely for these. Another is detecting image fraud and data integrity. You can actually embed an image inside an image by playing with just the last 2 bits of each pixel. And if people are interested, I'm happy to talk more about that. Can you tell if an image has been modified? If so, that means there could be a message placed there for a terrorist. All right, so general theory. So for many data sets, the probability of observing a first digit of 1 base b is the log of b, d plus 1 over d. So base 10, you get about 30% of the time. First thing you should do is check and make sure, is this a probability distribution? Well, if I take the sum of the logs is the product, is the logarithm of the product. So I would have 2 over 1 times 3 over 2 times 4 over 3, all the way up to times b over b minus 1, and I would get the log of b base b. So it's a nice exercise. Everything does at least add up to 1, and it is non-negative, so it's a probability distribution. So some background material. How many people have not seen Modulo Arithmetic? Okay, everyone has seen it. You may not have seen it with this language. So in abstract algebra, this is the language they would use. So it's 11 o'clock now. What time will it be in 5 hours? 16. Or 4. So I have 2 answers, 16 or 4. So on a clock, a standard cheap clock like we have here, not these fancy 24-hour clocks, 16 and 4 are indistinguishable because of wraparound effects. So we would say 2 numbers are equivalent mod C if their difference is a multiple of C. So here I did 17 is 5 mod 12, 4.5 is the same as 0.5 mod 1. So the significand of a number, if I give you a number x, I'm going to write it as some number between 1 and 10 times 10 to a power. So I'll assume my numbers here are positive. I'm not going to worry about the signs of my number. So if I give you 2017, oh sorry, it's 2018. 2018, it would be 2.018 times 10 cubed. And the k is not going to have any impact on the leading digit. It's just going to affect where the decimal point is. All right, so 2 numbers have the same significance if and only if x and x tilde have the same leading digit. And what's nice here is if I take the log of x base 10, that's the log of x, that's the log of the significant base 10 plus k. And the reason is when I take the log of a product, it's the sum of the logs. The log of 10 to the k is just k. So this means that the log of x base 10 is almost the same as the log of its significand. It differs by an integer. And this suggests that we should study these mod 1. So if the logs are the same mod 1, if they have the same fractional part, then when you exponentiate, they'll have the same leading digits. This also gives you an idea of where some advanced theory is going to enter. Fourier analysis. So e to the I theta is cosine theta plus I sine theta. E to the 2 pi I u is the same as e to the 2 pi I u mod 1. Because if I add in any copy of 1, 1, 2, 3, 4, negative 8, whatever, any integer number, when I hit it with 2 pi I go around a full number of cycles. And on the circle, I return to where I start. It's like adding multiples of 12 to my number on a clock. And this tells us why Fourier analysis is so useful in studying Benford. You want to get a sense of what mathematical ideas will allow me to make progress. Well, I want to take logarithms and I want to throw away the integer part. Taking a logarithm is no big deal. The log is a nice function. We've taken logs all the time. Throwing away the integer part of your logarithm, you can't just throw away part of the value of the function. Well, we can, as long as we are raising it in a nice way like this. And that gives you a sense of where these sines and cosines come into play. So the first idea we're going to really use is equidistribution. So we'll say a sequence is equidistributed mod 1 if the probability it lands in some subinterval AB inside 0, 1, and the limit is b minus a. So basically the fraction of the time we're in the interval AB is its length. If AB has length 1/3, then 1/3 of the time we should be there in the limit. If it has length 4/5, 4/5 of the time we should be there in the limit. So here's a beautiful theorem. If beta is irrational, then the integer multiples of beta are equidistributed mod 1. If beta is rational, well, it's a very different story. Let's say beta is 1/5. We'd get 1/5, 2/5, 3/5, 4/5, and then what's 5/5 mod 1? 0. What's 6/5 mod 1? So it would just cycle. So if beta is rational, you will cycle among finitely many values, and those will be the only things you see, and in the limit, each one will occur equally often. And the remarkable fact is that as long as beta is not rational, it will be equidistributed. It will fall uniformly. Now, how quickly does it fall? That's where advanced number theory and algebra comes into play. And there's a lot of nice questions. So the log of 2 base 10 is irrational, and the log of the golden mean base 10 is irrational. So I'll prove that the log of 2 base 10 is irrational. Assume not. So assume that this equals p over q, where p and q are in lowest terms. Then that means 2 is 10 to the p over q. Raise both sides to the qth power, so you get 2 to the q is 10 to the p. Well, 10 is 2 times 5. So we get 2 to the q minus p equals 5 to the p. This is an even number, unless q minus p equals 0. And what would it mean for q minus p to be 0? It would mean q equals p. It would mean the log of 2 is 1, not happening. 5 is an odd number, contradiction. So the log of 2 base 10 is irrational. As a nice exercise, prove that the golden mean has an irrational log as well. All right. So this is one of my favorite numbers, the square root of pi. So I ran a very dinky computation. I looked at the first 10 values of n square roots of pi mod 1. And I made a histogram plot and saw how many times was I between 0 and 0.1, between 0.1 and 0.2. I like the data. It's not too bad. Most things you would expect to have 1, but not everything is 1. If everything was 1, it would look a little fishy, like I picked the number. I don't want the data to look too good. Is this convincing to you that n root pi is going to be equidistributed? Okay, what would you like to see? More data. All right, let's look at 100. And again, you can start to see some fluctuations about 1. So you would expect about 10% of the time you should be in each bin. Here's 1,000. And now you need really good eyesight to see the fluctuations. So it's setting into equidistribution very rapidly. All right. So a data set is Benford base B if and only if its logarithms are equidistributed mod 1. So this gives you a really nice test for Benford. Rather than looking at the original data, do this logarithmic change of variables, chop off the integer part of the logarithm, and then see if what remains is equidistributed. So here's the proof. So let's write x as the significand times 10 to the k. So we take the log of both sides, and then when we look at things mod 1, this k doesn't matter. And that's why this is such a great thing to do, because I can now look at just the significand, which is what I want, and not worry about all the different zeros. So here is the plot. So here are my numbers 1 to 10, and then here are some logarithms down here. The log of 1 is 0. The log of 10 base 10 is 1. And so if I want to have a first digit of 1, then I've got to be somewhere between 1 and 2. Well, the log of 2 base 10 is about 0.3. So anything down here between 0 and about 0.3 will exponentiate and have a first digit of 1. And so that's the proof for the probabilities. Amazingly, I find that if you rotate it 90 degrees, the picture's a lot easier to follow. And so now I have my scales going this way. How you present data matters. That's one of the big points of today's lecture. So if I want a first digit of 1, I have to be somewhere between 0 and 0.3. And so what's the probability of having a leading digit of d? Well, if d was 5, I'd go from 5 to 6. So I would get the log of d plus 1 minus the log of d, and that's where a formula comes from. All right. So a nice example is 2 to the n is Benford base 10. What base do you think 2 to the n might not be Benford? Base 2, what other base?
Base 1.
Okay, we would not allow you to use base 1. Base 2, what other base?
Base 4.
Base 4. There could be some issues with bases that are powers of 2. Because we want the log of 2 base 10. If we had the log of 2 base 4, that's not going to be irrational. Fibonacci numbers are Benford. So we've been doing a lot with Fibonacci numbers. So here's the recurrence relation for the Fibonaccis. So we've talked about this many times. Guess an is r to the n. We get this nice characteristic equation. We solve the roots of 1 plus or minus root 5 over 2. Linear combinations are solutions. We can figure out what the values of C1 and C2 are by looking at the first 2 Fibonaccis. And we get the following beautiful formula. We've talked about this many, many times. This number is greater than 1 in absolute value. This number is less than 1 in absolute value. So when n becomes very, very large, this has almost no impact on the number. So you just have to do some bookkeeping. All the 1 over root 5 is going to do is going to just shift everything when I look at things mod 1. And I really have the nth Fibonacci number, when I take its logarithm, is basically n times the log of the golden mean. And the log of the golden mean is irrational, so we can use that result from before. It turns out that most linear recurrence relations are Benford. So the first one we're looking at 2 to the n, I can actually write that as an plus 1 is twice an. Now let's look at an plus 1 is twice an minus 1. This is a very carefully chosen recurrence relation. If I take a0 and a1 equals 1, then I get 2 minus 1 is 1. So every term would actually be 1. If I take a0 is 0 and a1 is 1, then the next term I get 2 minus 0 is 2. Then I would get 4 minus 2. No, 4 minus 1 is 3. Then 6 minus 2 is 4. So in this case, I would actually get an equals n. So in this case, I'm not getting Benford. And the reason is when you look at the recurrence relation here, the characteristic polynomial has a double root, r equals 1. And that's what's causing the issue. As long as I have exponential growth where the r is not 1, I'm going to basically be getting Benford. All right. So let's look at the first 60 values of 2 to the n. I've told you 2 to the n is supposed to be Benford. The numbers get pretty big pretty fast, so I'm only going to write the first 30. Already, let's see, 1, 2, 3. So already at 536 million at the 30th. Here's the digits. Here's the number of times we have that as a leading digit, the observed probability, the Benford probability. Good fit, bad fit. What do you think?
Good.
Good. Which are any of the numbers concerning to you more than others?
9.
9.
And 8.
And 8, but I think 9 is worse. So even though 8 is large, I like to look at things relative to the predicted value. So 0.83 percentage-wise isn't nearly as far from 0.051 as 0.017 is from 0.046. So percentage-wise, there's more deviation here. But this is the effect of small data. We've talked about this before. We looked at, for instance, teams in Major League Baseball down 3 games to nothing in a best-of-7 series. There's not that many data points. So to say that it was so unusual for the Red Sox to do this, and that it had never happened before, well, you're only expecting it to have happened once or twice already. And there might be a reason why no team has ever come back, because maybe you're not as good of a team as the person you're playing. So we've got to be very careful because the predicted numbers are so small here. What people sometimes do in statistics is you want to make sure every bin is at least 5%, or maybe even a little bit more. And maybe you might amalgamate 7, 8, and 9, or maybe even 8 and 9 together. And if you amalgamate 8 and 9, it's not so bad. So you really want to think about how you view data. I will highlight this in red as being bad. All right, so we have 3 people in computer science here. All right, I'm going to see how well you know your Greek and your Latin. All right, do you know what I'm going to ask you? How many megabytes are in a gigabyte? 1024. If you understood Greek or Latin, how many should there be? 1,000, right? Because you're going up by a factor of 1,000. 2 to the 10 is 1024. is almost 10 cubed. It's much more convenient because computers work base 2 to have 1,024 megabytes in a gigabyte, even though if you look at the Greek and Latin word, you would expect it to be a factor of 1,000. How does this play a role here? Well, imagine you lived in a world where 2 to the 10 equals 10 cubed. It doesn't, but imagine such a world. Every time I increase n by 10, I multiply my number by 2 to the 10, which is 1,000 in this strange world, which means I've just appended 3 digits. And in that world, when I go up by a factor of 10, I would now have 1,000, 2,000, 4,000. Not that different. In fact, if you look, every number here has the same leading digit as the previous columns. It's going to take a while before that small pollution is enough to change a digit. We haven't seen any 7s. We haven't seen any 9s yet. We're stuck. I don't think we haven't seen any 7s or 9s. Eventually we will, and we will see the correct behavior in the limit. So the IRS is very concerned about how rapidly does stuff like this set in. So I've actually done work with students for the Internal Revenue Service. I am not allowed to talk about what we've done. It is a situation where it's much better to make friends than to publish a paper. All right. So I chose 3 different numbers: the Euler-Mascheroni constant gamma, the Euler constant E, Euler rocks, and the number pi. And what I've done is for each one of them, I've looked at how close an alpha mod 1 is to being equidistributed, or equivalently how close things are to Benford. And I've calculated the chi-squared values. So this is looking at observed minus expected squared. Well, basically, we talked about this when we did Pythagoras. It's a measure of error. The smaller the chi-squared value, the better the fit. So when you look at this, which ones seem to be fitting well, which ones seem to be having issues?
E seems to fit well.
E seems to fit well. What about gamma?
Decent.
Yeah, I'd say pretty good. These are very low chi-squared values.
Yeah.
95% of the time you should be getting a value 15.5 or lower. These numbers are quite low. Which number has issues? Pi has issues, right? At first you think, well, it's basically getting better, but then it shoots up a bit. Does anybody here know digits of pi? Can anybody rattle off digits of pi? It's got to be somebody.
How many?
3.14.
1.5.
Can people? Can anybody here do?
9, 2, 6, 5, 3, 5, 8, 9, 7, 9, something.
Okay. How about pi squared? Lazy. I mean, you stopped at pi, really? You didn't look at any higher values of pi? Traditionalists. All right. So I'm going to plot log of the chi-squared because this will allow me to compress things. I'm going to plot it for pi to the n and e to the n. So pi to the n is red, e to the n is blue. And you can see the chi-squared values of e to the n are actually pretty small. The chi-squared values for pi have some interesting fluctuation. How would you describe the red pattern? Or at least approximately. So these are really good. The blue is really like 10 to the minus 1. That's a great small value. That's a really good fit. And so sometimes the values for red are down there, but sometimes they're quite high. When you look at this red shape, what words would you use to describe it?
Very consistent.
I'm sorry?
Consistent, even though it's...
Yeah, there's a little bit better word than consistent. Yes?
Periodic?
It looks periodic. With an amplitude that's getting smaller. I mean, you can see the jaggedness is even smaller. Anybody want to estimate the period? It doesn't have to be a perfect estimate. Give me an upper bound for the period.
200.
200. Give me a lower bound for the period.
150.
150. So give me a good estimate for the period.
185.
185?
180.
180.
55.
I'm sorry?
50 times pi. Or, I don't know. Oh, shit.
No, 50 times pi is too much. Any better estimates? All right, so we got about between 180 and 185. Pi to the 175 is 1.0028 times 10 to the 87. And this is why if you'd only spent a little bit more time in your childhood, You know,
Yeah, I could have gotten to that one.
I mean, really, I know it's, but I'm talking with admission, so I'm hoping by 20, 25, 26 we'll have a better. So what that means is every time you increase by 175, it is essentially the same as padding by 87 zeros. In fact, it's much better than 2 to the 10. 2 to the 10 was 1.024. This is 1.0028. And if you look at this, this is 100, here's 200, this is 150. This does look more like 175, almost like right between the two. Yes?
Why are we noting that?
Because every time we increase n by 175, we almost return to the number we started with just 87 zeros at the end. If pi to the 175 just equaled 10 to the 87, we would just be adding 87 zeros at the end.
Right, but why is that exciting for us?
Well, because that explains why you have this periodic behavior.
Okay.
Because every time we increase n by 175, we almost return to where we started. Because we're not quite there, that's why the things are getting a little bit better. That's why the amplitude is getting a little bit smaller. And again, I want you to be able to look at graphs and tell a story. Yep. This is one of the things you need to get out of a math class or a statistics class. How can you look at data and say something meaningful about it, especially to bosses and people with money? Yes.
So as you increase the period, the first, the second, third.
We're not increasing the period because it's not periodic. It's almost periodic. As you increase n.
As you increase n, how come the amplitude goes down, 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 down? Is it
Because
you
it's
have the
not
left number?
exactly 10 to the 87.
If it were exact.
Then it would be perfectly periodic.
Okay.
And that's very similar to when we had the stuff with the powers of 2. If it was exactly 10 cubed, it would be 1, 1,000, etc., 100,000, or maybe a million. But because it's not perfect, it's going to be getting better and better and better, getting more and more Benford. Okay, so why Benford's law? So I want to give you some ways to see Benford emerging. So imagine you have a long street, and the houses are numbered from 1 to L. If the street stops at house 199 or the street stops at 999, very different answer for how often is the first digit 1. Here, it's going to be essentially 5/9, and here it's going to be essentially 1/9. So the probability of having a first digit of 1 is going to fluctuate. We've just had more than half of our streets starting with a 1. So if I plot the probability of a first digit of 1 versus the street length, we get some curve like this. And we can see that as the street lengths get longer and longer and longer, it's going to take longer and longer. Yes?
So this law only works if we assume that whatever number we're looking at has been counting, like a street number or money you have to start from 0.
It works for lots of things. It works for values
Yeah.
of special functions.
But it wouldn't work for a random number.
It works
correct?
for certain types of random numbers. And so there are a lot of random processes that will obey Benford's law as well. But you're talking about you need a huge number of data points sometimes before you start getting good convergence. It can take a while for the limiting behavior to kick in. And this is the biggest question the IRS cares about. How many data points do they need before they are confident?
What was that?
North Korea.
No, somebody didn't hand in their homework. So when you look at this is not a natural way to look at this. Anybody have any idea what I should do to make this an easier plot to look at?
Logs.
Yeah, take logs. Actually, just take logs in one direction. And now, notice how these are going to basically be the same size. Because now all I care about is going from a street of 10 to the 4th, 10 to the 5th, 10 to the 6th. It just matters where do I stop and chop. All right. What if we have many streets of different lengths? So in the first situation, I'm going to take 100 streets, and each street is going to have houses from 1 to 10,000. Not surprisingly, all my digits are going to be equally likely as the starting digit for street houses, as well as same for the first two. Now, let's take 100 streets, and each street length is going to be a random number from 1 to random 10,000. So I'm going to choose uniformly a number from 1 to 10,000, and that will be my street length. And now look at all the houses on that street. Then I'm going to choose another number uniformly from 1 to 10,000. And you can see it's closer to Benford. I can do random 10,000. And it's even closer to Benford. Yes.
What does that mean, random?
So I choose the number randomly from 1 to 10,000, and then let's say I chose 58. Then I would choose a number randomly from 1 to 58.
Okay.
And so the more times I iterate this, the more randomness I have in the process, the closer it is to Benford. You should have seen this picture so many times now. We have a probability distribution. It's non-negative, integrates to 1. Probability on between A and B is just the integral under the curve from A to B. The mean is x times p of x. The variance is x minus mu squared p of x. Independence knowledge of one random variable gives no knowledge of another. All right, so here's the normal. This is the central limit theorem, the big result of the class. If we look at the sum of independent identically distributed random variables, subtract off n times the mean, divide by sigma square roots of n, that should converge to being normally distributed. So we're going to see another application of the central limit theorem today. So we've seen this picture before. Here is the uniform distribution comparing it to a normal. Sums of 2 uniforms, sums of 4 uniforms, sums of 8 uniforms. Very hard to see the difference between that and a Gaussian. And this is one of the things I really want you to take away from this course as to why we can use the central limit theorem. Because the error is so small so quickly that for a lot of purposes, it's not a bad approximation to say, we will replace the complicated true behavior with this approximate behavior. And again, what's the number you learn as wholly in statistics for the number of points you need?
30.
30, right. If you have 30, for the most part, you're safe. We've talked about how painful it is to write down the explicit formulas, but it can be done. This is the sum of 4 uniforms. So I'm looking now at a normal distribution, mean 0, variance sigma squared, and as the variance gets larger and larger and larger, if I look at the normal distribution mod 1, it converges to a uniform. So here I'm looking at the normal where the variance is 0.01. 0.01 is a very small variance. If the variance is 0.01, what's the standard deviation? 0.1, 1/10. So it's really tightly. And so not surprisingly, well, if the standard deviation is 1/10, you don't expect to be more than 2 standard deviations away. The mean is 0, here's 0.2, and going negative 0.2 is going like that in this direction. And you can see, yes, most of my mass of the normal mod 1 is going to be very close to 0. And I claim that as we increase the variance, it's going to converge to being uniform. So here's the variance is 0.1. That's not that bad. Unfortunately, when I increase the variance to 0.5, it looks very bad in terms of how far apart it is. Is this upsetting?
Your axes are off.
Yes. This is why we have emphasized numerous times, thou shalt label thy axes. Right? If you look 1.0001 to 0.9999, yes, it looks like there's a big dip. But if I were to actually plot from 0 to 1, you would not be able to see the difference at all. So always be aware of what the label of your axes are. All right, so we've done this many times. If you see a product, take a logarithm. So let's say we have some observation that's a product of independent identically distributed random variables. Well, let's let yi be the log of xi, and let's let vn be the log of wn, the log of the product. Well, vn is the log of the product, so it's the sum of the logs. Oh, what should the sum of the logs converge to? What theorem should we be using here? Central limit theorem, right? This should be converging to being a normal with increasing variance. Well, to see if something is Benford, we take its logarithm and we look mod 1. So we have something that's converging to normal with variance getting larger and larger and larger. And so this is converging to a uniform when we look at it mod 1, and that's why we have Benford. So this is at least one reason why so many places are Benford. All right, some applications. I am not going to go into detail because this is being recorded, but there are 2 different Steve Millers. One of them still has the job that they had when the pictures were taken. So I will leave that as a Google search exercise for you to figure out who is the other Steve Miller and what did he do wrong. I will not go into details here. You can pause and you can look at those. I will just say one of my colleagues has a wonderful quote. It is amazing what a couple $100 in the Freedom of Information Act will buy you. So I'll let you look at those later at your leisure if you so wish. So here's one of my favorite examples of Benford's law. There was an audit at a bank, and it revealed a huge spike relative to what was predicted of numbers with a leading digit starting with what?
9.
No.
1.
No.
7.
No, but you're closer.
8.
Nope.
6.
No.
5.
No.
4.
Yes, 4.
There we go.
There you go. A lot of them with 4.
Good job.
And so they then investigated a little bit further. They looked at all these numbers that were starting with 4, and they found the second digit was very likely to be
1.
no, opposite direction.
9.
Yes,
No.
8 and 9. So there were a lot of transactions in this bank with 4 8s and 4 9s. And in fact, a lot of these were coming from one person. Does anybody here have a credit card with their name on it?
Does
Take it out.
debit work?
I'm sorry?
Does debit work?
Debit would work.
I think 2's not going to hurt.
Thank you.
Do you want 2?
No, sure.
it's-
No, I'll just take one.
I hope he doesn't
All right.
need that.
Yeah, so poor Franklin, okay, he just lost his credit card. So can people keep him busy for the next few? No. So what should he do?
Call the bank.
Call the bank, right? Debated actually taking an older credit card with me today to see, but yeah, I assumed he'd be smart enough to check.
This is my card.
Yeah.
Wait a second.
So he calls up the bank and says, my credit card has been stolen. And the bank says, don't worry, you're not liable for the charges. Now you're the bank. Do you track down who stole the credit card?
Yep.
Always.
Hunt him down.
Hunt them down. I like this idea of justice, but let's say you're the bank. It's expensive to track someone down. Let's say there's $3.14 to go back to pi in disputed charges. Is it worth hiring an agent to track this down? No. Let's say somebody just bought 10 Lamborghinis. In that case, we're going to find them. So what a lot of banks did is they had a floor. Anything below $5,000, the person could just write off without an internal investigation. Anything above $5,000 generated an internal investigation. What was happening here is one of the workers on the credit card line was having their friends sign up for credit cards and run up debts of $4,800, $4,900. And then call, oh, I'm so sorry to hear your card was stolen. Don't worry, you're not liable for any charges. And they could just write it off without triggering an internal investigation. What should you do if you're the bank in the future?
You can randomly audit.
You have to randomly audit. Now, what you might do is you might say, I will audit 100% of the time anything that's above $10,000. 90% of the time anything that's above $7,000, and so on and so on. So that if it's $1,000, maybe you only audit that 10% of the time. When you have security lines at airports, if you see an elderly grandmother in a wheelchair with her arm in a cast and a little grandkid, do you still have to give her extra security?
Yes.
Yes, every single time. Probably not as often as the person wearing a shirt saying, death to America, maybe. But if there is a category that is never investigated, then you've just told people, here's a opportunity. So it's, how do you allocate your resources? And there's a lot of interesting discussions on this. Yes?
When you say audit, what?
So what I would say for the bank is I would investigate and not allow the person to just write off the $1,000 in stolen credit.
But what does that look like when you say
It would mean you would have to hire an agent to try to track down who stole the credit card, where were the charges made, and see, did the person who is calling the credit card as stolen, did they make the charges?
Right.
So you don't want to say that there's a certain choice that will never be investigated, because that is a suggestion to certain people that, hey, if you try to do this, we're not going to check. So there was the write-off limit. All right. Here is 130 years of stream flow data that I analyzed with my colleague Mark Negrini. You can see terrific fit with Benford's law. Yes?
Do banks release that information publicly?
There is some information they release. And in fact, when my student gave her talk on Benford's law earlier this semester, she actually talked about the N1 data. And if you looked at the N1 collapse, there was a lot of evidence, if you did some of these Benford checks, that their books had issues. There's been some checks with some nations in the European Union in terms of the numbers that they send to central planning. Greece in particular, I think, has been flagged. I'm going to just leave this here. I'm not going to talk about array and elections. So we've got zeta of s 3x plus 1 in stick decomposition. I'm going to do stick decomposition first, because this involves more of what I've done with some students. So imagine the following decomposition process. You take a stick of length L, and in the simple model, we're going to uniformly choose a probability between 0 and 1, a proportion. And we're going to always use that same proportion. In the more complicated model, which we've analyzed, we allow the proportion to change at each time. And we're going to split the stick at P. So we'll have one stick of length PL and one stick of length 1 minus P times L. And then we'll break this stick again into two sticks at P% of the way down, and same for the other. And then we're going to look at the distribution of the leading digit of all the stick lengths as we go further and further down. And the claim is that for almost all P, this should be Benford. Can you give me a value of P where you do not expect Benford? The distribution of stick lengths. There are three numbers. Yes? 0, because then you just always have the same stick.
Infinity.
Well, you can't do infinity.
1/2.
1/2 and 1. So if you do 0 or 1, you're not breaking the stick. And if you do 1/2, all the sticks always have the same length. So the conjecture was that as long as you don't take P equals 1/2, as you go through this, as you go further and further down, it will become Benford. So here, for instance, is P equals 0.51, which is pretty close to 1/2, not Benford. I'm sorry, very close to Benford. Sorry, very close to Benford. Conjecture turns out to be false. So if you take P equals 1/11, you actually get something that is not Benford. And so here's the reason. So at the nth level, we have 2 to the n sticks. We have n plus 1 distinct lengths. The lengths are going to be P to the n, and I'm going to write it in a nice way, 1 minus P over P to the j. So you can write this as P to the n minus j, 1 minus P to the j. You should recognize this from the binomial theorem. And the reason to write it like this is now all the stick lengths are P to the n times a power of this factor 1 minus P over P. Imagine this factor 1 minus P over P equal to 10, or 100, or 1/10, or 1 over 100. Then you would just be padding zeros, and all the stick lengths would have the same significance. It's a little bit more interesting because not all of these occur with the same frequency. The frequency is n choose j. But you can deal with that. But it tells you that there's going to be an issue if 1 minus P over P is related to a power of 10. So if 1 minus P over P is 10 to the y, where y is rational, then it's not going to be Benford. And if you remember, I gave you 1/11. 1 minus 1/11 is 10/11 divided by 1/11 is 10. And that's where the 1/11 came from. So here's P equals 3/11. The corresponding value of y is irrational. It looks pretty close to Benford. Here is P equals 1/11. And if you look at the distribution of leading digits, you can see this is most assuredly not Benford. All right, let's do 3x plus 1. Have we done the 3x plus 1 problem yet in this class? So two of my favorite quotes, one by Kakutani. This is a Soviet conspiracy to slow down American mathematics. Because when he would travel to different universities and give talks, he would mention the problem, and people would say, oh, that's not so bad. And then after a month, they'd give up in frustration. Erdős said mathematics is not yet ready for problems like this. So the way it works is you have some number. We'll assume that the number is odd. And then I multiply by 3 and add 1. And then I divide by as many powers of 2 as I can. You sometimes break it up into 2 steps. If it's odd, multiply by 3 and add 1. And then if it's even, divide by 2. What this does is it just does everything all in one step. So for instance, if I start off with 5 is odd, so I would do 5 times 3 is 15 plus 1 is 16. So I would then send 5 to 1. And 1 is odd, so I go 1 goes to 4, oh, that goes to 1. So once I'm at 1, I stay at 1. And the conjecture, in fact, is that no matter what starting value you take, there is some n such that eventually, if you iterate n times, you'll be at 1, and then you'll stay there for all eternity.
What's the notation for the vertical bars?
The vertical bars means it doesn't just divide, it really divides. So it's the highest power of 2 that divides 3x plus 1. So for instance, if I give you 30, the highest power of 2 that divides 30 is 1. 4 does not divide 30. So I would say 2 double divides 30. If I gave you 20, I would say 4 double divides 20.
And that's with no remainder.
And that's with no remainder.
Okay.
So 7 is odd. So 7 would go to 11, and I'm going to pull out 1 power of 2 because I go to 22. 11 is odd. When I pull out powers of 2, I get 17. I pulled out 1 power of 2. And I keep iterating like this, and this shows you that at least when I started with 7, I iterate down to 1. And then I stayed 1 forever. And so these numbers tell me how many powers of 2 I pull out. And so if I look at just the first 2 in my chain, that's a 2 path. If I look at the first 5, it's a 5 path, and so on and so on. It turns out that these powers behave like independent, identically distributed geometric random variables. And so we can do a lot of analysis. I'm going to skip the slide in the interest of time. And I was able to prove that if you look at where you are after m iterations and divide by where you expect to be, that that's Benford. And when I gave a talk at Michigan, one of my colleagues, one of my brothers, in fact, proved with one of his colleagues that, in fact, not just looking at where you are relative to where you expect, but if you choose a fixed starting seed and iterate a large number of times, then with high probability, you are close to Benford every single time for each seed. So just to give you, some sense of the data, here's looking at 80,000 iterations, starting with a 10,000 digit random number, looking at the observed probabilities and looking at the Benford probabilities and just seeing the remarkable behavior. There is a huge amount of theory to this. So I'm writing that it took us 80,514 iterations before we got down to 1. There's a theory that predicts how much it should be, and the prediction for a number of that size is it should be roughly 80,319. Remarkable agreement. This is just the tip of the iceberg. But what I want you to get from this is applications of what we've been doing. Central limit theorem is extremely powerful. It allows us to analyze other problems. It gives us some idea of why we see this. Huge part of the course is looking at data the right way. Benford's law of digit bias actually becomes the law of equidistribution if you look at data the right way. How do you look at the data? You take the logarithm and then look at that mod 1. We're not going to do that for most data sets. If I ask you what is the temperature, what is your grade on the exam, what is someone's batting average, you're not going to take the logarithm and then chop off the integer part. It doesn't make sense. But when you're looking for a lot of behavior and how things are distributed, it's actually a very good way to go. Another big idea is what techniques will be useful to solve things. And I'm not going into it right now, but if you're interested, let me know and I can give you some survey articles to read. Fourier analysis is extremely useful because e to the 2 pi I u, it doesn't care if I take u or u mod 1. And that gives you a clue of how we can attack problems like this. This also has tremendous applications. It is used to detect fraud. It's also used for data integrity. Maybe no fraud is happening, but maybe the data is not being collected properly. It's a great way to flag that something is going on. It's also another example of the more random something is, the better the limiting behavior, or the more we can say about the limiting behavior, because things are essentially averaging out.
So you know all this. If someone wanted to hire you, could you cook the books?
So it is now time to conclude today's lecture.